Hi, and welcome back to Principles of Data Management. This is going to be the lecture on data analytics. A caveat before we get started on this lecture in that this is literally a one video overview of data analytics. This is not my forte, and as a matter of fact, we have an entire class dedicated to this topic. That would be CSCI 420 or CSCI 720. My goal here is to introduce you to the topic and get you engaged in the topic rather than to teach you the specifics of how data analytics work. So with that, let's get started. So the basic process of why we do analytics is to basically prepare the business to make better decisions. So we have to identify a problem, figure out where we can get the data from, do some cleaning of the data, analyze the data, and you get some results out of it. So what are some examples of our applications? Well, there's a couple different categories. Risk analysis, so determining if you should give somebody a loan for like school. Fraud detection. Credit cards use this frequently. The idea of you go and spend $5,000 at Best Buy and you've never stepped foot in a Best Buy before, well, that might be fraud. So marketing analysis, churn prediction, whether people will continue your services, response modeling, understanding what customers want, and then customer segmentation, so delivering the products that customers want in the areas that they're looking for them. Recommender systems, Netflix, Spotify, where they recommend TV shows, movies, or music to you, and text analytics, understanding the meanings of text that you didn't before. So there is a chart here of different types of analytics, and certainly something that you should be aware of. You don't need to know all these terms, but understanding like government analytics would be detecting social security fraud or detecting terrorism. Web analytics is basically how your search engine works. Logistics, demand forecasting. So UPS has to know when Prime Day is so that they can make sure enough trucks are on the road and airplanes are in the air. HR analytics, understanding where people are going to work and how they're going to work and whether people are going to leave or stay. Healthcare analytics, understanding what treatments to give people. Learning analytics, same thing, how people learn and work within those models. And we looked at a lot of marketing examples already. So there's a couple different jobs here. A data scientist is generally involved in the machine learning and the statistics side of it. They often do some programming and they have business knowledge and creativity. So they are the ones presenting the charts to the business folks and understand what their needs are and how they work, and presenting the data in new and interesting formats. So data pre-processing is about denormalizing your data for analysis. We spent an awful lot of time talking about normalizing data. Well, for analytics, we typically denormalize, mostly for performance, and because the data doesn't change, the idea of normalizing doesn't help us. We're going to do sampling, which we're going to talk about here in a second, exploratory analysis, find missing values, and how we handle outliers. So denormalizing here, we take our data, join it together, we get some duplicate data, no big data, no big deal. It's just easier to analyze. So what is sampling? Sampling is taking a subset of that data and using it in your model. So a good sample should be representative of the data. And so it says instead of just picking, let's say we have historical data from 1900, picking all your dates from your sample to be from 1900 to 1901 isn't a good sample of your analytic model. So you have to pick specific results. And remember that the window for that sample is going to be a trade-off. So if you pick 50 entries, you may not get every year, for example, from 1900. But if you pick too many years, it's going to be expensive to compute your sample. So exploratory analysis is about running some initial analysis, whether you load it into an Excel spreadsheet and create a histogram or a bar chart or whatever, and just understand, does the sample data give you what you think you're going to find? Some things we might do: mean, median, mode, standard deviation, percentile values. Again, nothing too fancy. So what do we do about missing values? Well, there's a couple different choices here. And here we have a couple of missing values on income and marriage and credit bureau score and whether or not fraud was committed. So what are our choices? We can keep the missing values, we can delete the entire thing, or we could replace it with something else. So we have, we'll go back here. So marital status. What we might do is take all of our unknown values and convert it to single, because that's sort of the baseline. The credit score, maybe that's not a good choice to put something in. And then same thing with income, is you may not have a good idea of what that should be. Now, when we do our analysis, for example, we may want to remove everything that doesn't have a marital status. And that would just be removed from our records altogether. So those are our three basic choices. So outlier detections. So are they valid or invalid observations? We need to figure that out first. And then how do we detect it? Well, minimum, maximum values. We could do histograms, box plots, so on and so forth. And then how do we treat them? And it goes back to the same choices that we have with missing values. So we just cap them, treat them as missing. For example, an outlier might be something like the age of your customer, and you get somebody that's 102. Well, that would be an outlier for a variety of reasons, but the question is, do you include it, cap it, and say that if any person is over 90, we treat them as 90, or do you just delete it altogether? So there's a couple different types of analytics that we're going to focus on here: predictive, descriptive, and social analytics. So of our predictive analytics, we can do linear regression, logical regression, decision trees, and there are others. Linear and logical are very related. And again, I'm not expecting you to know these formulas in this class, but what you get is basically a linear line that represents the average of your data in the X and Y coordinates. This is something you can do in Excel pretty easily. And then you pick a new X value and see where it would appear on that line in the Y. And that is your prediction. Logical regression, on the other hand, produces a logical line, which works the same way. So you basically pick an X and a Y value and then compare it to where it should be on that line. So here we have a simple logical regression that indicates best fit for income versus age. And as you can see, there are some invalid results here. So we have a no in the yes side and some yeses in the no side, but it is a good representation of where the split is. So the odds amount and doubling amount, or odds ratio and doubling amount, is not something you need to be familiar with for this class. Which gives us takes us to a decision tree, which is basically a tree, a binary tree, whereby which we make a decision based on a value at a point in the tree. And then here we have a decision tree that says if our income is below $50,000 or above, and then if you're employed or not, and then what your age is, and whether or not you will, for example, respond to a survey. When we do our decision trees, we have some interesting things to think about. So what do we split on? So going back here, do we split on income? Maybe that's a good thing or not a good thing. Do we care if the respondent is employed? We have to think about when we stop adding nodes to the tree. So going down here on the left, do we look at income, employed, and then look at how many cars you own? And where do you actually stop creating your tree? And then what do you assign to a leaf node? So what is our leaf node values here? So what we're looking for is the minimal impurity. So when we pick a side, it is the correct value. And this basically represents that. So what we're looking for is the correct yes versus the correct no, the good and the bad, or the gin and the entropy. So here we're going to split. We have 50 in the top node, or 400 400 of going left and right. And then we can, from there, pick, when we went to the right side, they were all G, which is basically not a good scenario because there was no reason to go to the right in that situation. Versus the one on the left where we have a 200 400 split, we have a much better result because we can make a decision based on where they went. Which brings us to this. So the idea here is what you want is the best distribution of results in a decision tree. So this line represents our validation set, and what you end up with is as we keep adding nodes, we will get more and more misclassifications. And we don't really want misclassification, so what we're going to do is look at this, and this is where we stop growing our tree, is where we start misclassifying things at a higher rate. And that's really what you want to look at. So here is a decision tree shown in a flat chart, and it shows you all the yeses here, which is very low entropy, very few Y's here, which is very low entropy, and then mostly yeses here, which is good. Regression tree is the idea of very similar to a decision tree, except we have multiple nodes here, and we get a rate as opposed to a simple yes-no result. And again, math, which I'm not concerned with in this class. So we have other predictive analytics techniques as well. Neural networks, support vectors, deep learning, and all of these are covered in depth in 420. So how do we actually evaluate them? Well, we're going to look at splitting our data into two different categories. We're going to measure it and look at that from here. So first thing we're going to do is split it into training and test sets. So your training is what you do to train your data to make sure that you created the right decision tree or linear regression model, etc., etc., etc. Then you run that model against your test data and see how good it is. Generally, you do a 70-30 split on your data. So you'll train with 30 and test with 70. And again, that's not fixed. It's just a common approach. So how do you actually split it? Well, some people will split into segments and run it and see what happens. Bootstrapping. So let me go back to here. So the idea is you could basically take a segment of your data, train it, and then validate, or train it with this white box and validate it with the gray box, and then do the same thing again. Train it with the white box and validate it with the gray box, and do that with every segment of data. The other option is your bootstrapping. So you take your data, and put it in a particular order, then run it in a different order and see what happens. So that's the basics of predictive analytics. Now let's look at descriptive analytics. We have association rules, sequence rules, and clustering to cover. So association rules are associating one thing with another. So for example, you go and buy beer and you go and buy baby food and diapers and milk at the grocery store. You might also buy beer. So that would be an association thing. So you did X, Y, and Z. You'll probably also do A, B, and C. Music services will do this, like Spotify. If your friends like song A, you may also like song A if you both liked one other song. So here we have support, confidence, and lift. And what this gives you, again, I'm not too concerned with this number, but what you have is the total number of transactions that support the union of X and Y. So when you buy Mentos, you also buy Coke, versus all the transactions that you've bought at the grocery store is your support. Confidence is the union of Mentos and Coke versus just the purchase of Mentos. And lift is your support of Mentos and Coke over your support of your Mentos and your dot product of Coke. So what we need to do is filter out some trivial rules. So the idea of trivial rules is that when you, for example, go into a grocery store and buy apple cider, you're probably also buying donuts. So that would be a trivial rule. Everybody knows it. So we ignore that. Sensitivity analysis, you don't want to get too specific. You want to be able to visualize things and measure the economic impact. So this is just an example of a sequence rule. So we have sequence ABC, then BC for different sessions. So it's the order that people did things. Let me go back to there again. So sequence rules are the idea that, for example, when I'm going to pick the grocery store again, you go to the grocery store and you go to the produce section, then you go to the bakery section, then you go to canned goods, then you go to frozen goods. So we're looking at the order that you did things. You wake up in the morning, you go to the coffee shop, then you go to class. The sequence that things were done. So we have some different clustering rules we're going to look at here. We have non-hierarchical and hierarchical. K-means is extremely popular and divisive is as well. So clustering is grouping things together. So here we took C1, C2, grouped them together, took C4 and C5, grouped them together, and we eventually grouped everything together at the very end. So we know that C1 and C2 were more related than C4 and C5 were. So we look at distances here for clustering. We have the Manhattan distance versus the Euclidean distance. And Manhattan is going around. Much like in Manhattan, you have to go around a block. You can't go through a building typically. And Euclidean distance is your straight line. So what we have for clustering is we can have a single item linked. A single linkage. We link the closest items together. Complete linkage is linking the furthest items in a cluster together. Average linking is linking every item together. And then centroid is averaging every item in a cluster and comparing it to the average of every other item in a cluster. So what we have here is clustering of birds. And we're going to say a chicken and a duck are very related. And then those two are slightly related to a pigeon. A parrot and a canary are very related, which all those things together are more similar to each other than an owl and an eagle are to them. But they're all birds. So we classify them that way. So k-means is the idea of selecting our initial seed, and then we're going to move to the closest items, and we didn't even do that. So, oops, let's go backwards. So in a k-means, the idea here is that we're going to do, we have a points on our map. And what we're going to do for k-means, see if we can get a different color, see if it even shows up, is put a initial cluster here. Say this big dot here, and put another one over here. And then we're going to move each of these to their nearest centroid, or nearest node. And the idea here is that this will then move somewhere, and then we recalculate until we get everything into their own cluster. And that's basically it. So social networking analytics. Obviously, social networking is a big thing, so we're going to look at this, but again, we're going to go through it pretty quickly. So social networking has nodes and edges. Nodes could be a customer, a user of your product. Edges is how they are related to each other, whether they're following their family, they transmitted a disease, and so on and so forth. And this is just a simple social networking graph. So a sociogram is how those things are related. So in this case, C1 is one step away from C2, and so on and so forth. We could look at the a couple different properties of our social networking. The geodesic, which I can never say correctly, but the distance between two nodes, degree, number of connections between them, closeness, how close are they, shortest path between two nodes, and so on and so forth. So what we're looking here, or what we see here, is a social networking metrics for a bunch of different people. And there's a couple things that you're going to see. First off, Diane is closely related to a bunch of people. So what you have is she has 6 degrees, 6 people connected to her. Closeness of 0.64 is Fernando, which is indicating that he is close. And then, am I looking at this wrong? Yeah, no, we're good. And then the betweenness between her and Heather, there are 14 nodes that connect her and Heather. Jane, on the other hand, is not connected to anyone other than Ike, so she has a very low betweenness score. Featurization is the idea of detecting churn or change in values. So we want to know, in this case, how do people who respond to something, are they going to respond to something else, is basically the idea. So we're going to look at this chart here, which says John has an average revenue of 123. He did not receive promotion. The average age of his friends is 20. And then we look at, do his friends get promotions? No, they're likely to not respond to them. So we're looking at how the friends relate to what you are going to do. So we are going to look at some post-processing here, and that'll get pretty close to wrapping this up. So we need to look at business relevance. So do these decisions make sense? Is it justifiable to look at these? Is there an economic cost? Is there regulatory compliance in all of our analytic models? So the economic perspective, what is the cost of ownership? The cost of owning the data sets to do this. What's the return on investment? So can we sell more products? Can we market products better? Should we get somebody to outsource this analytics, or can we do it in-house? Should we use an on-premise versus a cloud service, and then open source versus not? So cost of ownership, the idea of you have network and security costs. I already mentioned this. Startup costs, archiving costs, replacement costs, downtime costs, insurance. Oops, I'm skipping way ahead. And so on and so forth. Your return on investment. More details here. So can you get better sales, lower fraud, better fraud analytics, automation of decision making, so on and so forth. So, so return on investment. This is just a chart showing how many people thought they would get a good return on investment. Again, not particularly relevant. So in-house versus outsourcing. When you're outsourcing, somebody else is going to do the data collection, cleaning, processing, and so on and so forth. So what is the risk of that? Well, somebody else now knows your strategy. They may have access to confidential information. What happens if the partnership is broken? What happens if you have a cultural mismatch, which, again, that's interesting analytics there. And then shortage of data scientists. So you're basically outsourcing it to somebody else that may not need it. So when we do on-premise analysis, we have full control, but we have to worry about security. And then what happens if our business grows? We need to have a growth in our systems, which may be expensive. So cloud systems have better security overall. Scalability is high, but their cost is also high. Open source versus commercial software. This is a tried and true argument with software developers for all time, so I'm not even going to get into that. So how do we improve our return on investment? Well, get new sources, get better data. We can send data to other people. We can look at that as well. So what does it mean to get new sources of data? Well, we can get public data. There's lots of public data out there. We can get implicit data from our network connections, etc. And network, I don't mean computer network, but network between people. We can look at location data, so on and so forth. But all this means is that when we get garbage in for our data, we're not going to be able to do good analytics. So the causes of bad data, and this is, I've definitely experienced this, is very much rooted in processes and culture. So if you are unwilling to look outside the bounds of what your data is trying to tell you, or what you think your data should tell you, you're not going to find anything new and interesting. So what we really need is transparency between what the data is trying to show us and how we can actually do it. So we also need, when we're doing data analytics, support from different management teams in order to let the data analytics do what they need to do, again, rather than trying to prove a already existing model. So governance, we talked about this in a previous lecture, I believe, but you have centralized, decentralized, and mixed. So central, well, not in the same manner, but centralized is that data scientists are going to handle all data requests or analytics requests, versus decentralized, where a data scientist is assigned to a business unit. These have pluses and minuses. So with a centralized model, when you have the entire data scientist group handling all requests, there can be the idea of cross-fertilization, which we're going to talk here. The idea of a data scientist will see how one business unit is doing something and can share that information with another business unit. Decentralized, on the other hand, means that a data scientist can focus solely on that business model and maybe come up with more interesting results. And then we have mixed, which means that we do a hybrid of them, and it, in theory, provides the best of both worlds. So cross-fertilization, the idea of looking at different things across the organization. So privacy and security, the idea of what is data security. So protecting the confidentiality of your data. So policies where not every user in your organization can access social security numbers. You need to have data privacy. So if you're agreeing to not share information with third parties, that's data privacy. HIPAA and FERPA are about data privacy. Data security, again, guaranteeing data integrity, availability, authentication, confidentiality, auditing, and vulnerabilities. Mitigate them. So we'll skip that. So when you access data internally, oftentimes you want to do things with anonymization so that people can't find out who individual users are. This can be done with SQL views or label-based controls. So with anonymization, we can do things like aggregation, discretization, value distortion, and generalization. So anonymization, here we have a good example of where we need to anonymize data. We have names on here, and instead of including the names in our anonymized view, we just have IDs, which can't be tied back to a person. And then doing that with a SQL view, and I think we had... Yeah, so I wanted to go through these. Discretization, the idea of changing a value. Value distortion is grouping or changing a value to something irrelevant, but keeping it like just multiplying it by 5 for your income. You don't tell people what is being multiplied by, but it is distorted from the original value. Generalization is the idea of grouping things together. So ages. So you say 18 to 25, 25 to 33, 34 to 40, and so on and so forth. The idea of generalization. So you put them in groups rather than having specific value. SQL views can get data from different places and limit access to particular fields. And then label-based access controls is the idea of creating roles who can access what data and when. And again, I'll let you read over these in your own time. This has already gotten a little long, so we aren't going to go too much further. Privacy. In the EU, the GDPR is a very tight privacy regulation. Most companies will comply with the GDPR, which means that in the US, most things are GDPR compliant because most companies don't want to have multiple privacy policies. Again, I have thrown a lot at you in 35 minutes, but we have entire classes dedicated to this topic. If any of this sounded interesting about how you can do different analytics on data, be sure to look into taking 420, 521, 421, 720, and so on and so forth. Those are all good classes on data analytics, cleaning, and analysis. Anyway, with that, I hope this made sense. Feel free to certainly look at the book for this particular topic because there's some more details on some of these analytics which might be useful to you. As always, have a great rest of your day, and we'll see you next time.